Voilà, je suis nouveau là. Discretization method is it's the most popular method for the wave equation, I would say. And then I will explain what the CFL condition is. Again, I believe this is to motivate what I'm doing, and probably it is known to many of you. And then I will really explain a little more in the how to derive local time-stepping methods, so which is abbreviated by LTS for Ramacutta methods. And then I will say something about leapfrog-based local time-stepping methods, which are actually older, but I'm not going to get into the details here. And then I would like to show you some parallel results to convince you that this is an interesting approach. So this is the model problem that I'm looking at, but again, it's just one model. It's not like the only equation that I look at. So this is the wave equation. If sigma is 0, then it's the classical wave equation. U is the unknown function, depends on time and on position x. We have c. C is the speed of propagation, which usually depends on position, and it depends on the material or the medium where the waves are propagating. And sigma could be a damping term. Sigma can also be 0, of course. And this is the weak formulation. So we multiply the equations by test function v, we integrate by parts, and then we end up with this, again, standard weak formulation of the problem, where we have the appearance of the bilinear form AUV here, which is the standard bilinear form, simply C grad U grad V. And it is also well known, of course, if the right-hand side, so if there's no forcing, and if sigma is 0, so if F and sigma are both 0, then the total energy of the system is conserved. So there is a desire, at least for certain situations, to construct methods which are energy conserving. And yes. So how do we go now to derive a numerical method? Well, we take this weak formulation and we replace the continuous underlying Sobolev space H01, for instance, by a finite dimensional subspace VH. So here I'm choosing polynomials of degree L, which live on these triangles or tetrahedra in 3D, which I would denote by K, and they belong to the mesh tau H. And here I'm doing conforming finite elements, but everything I say you can also use for, I've used this also for discontinuous Galerkin methods. So if you use standard Galerkin formulation with standard finite elements, you end up with this formulation, let's say here with sigma equal to 0. So this would be the wave equation in its semi-discrete Galerkin formulation. And you need to project, of course, the initial conditions. Maybe you do an L2 projection, maybe also you just interpolate it. And this formulation automatically inherits the properties of the continuous formulation, which means that this formulation is also energy conserving automatically because that's, if F is 0, of course, because the bilinear form is symmetric. Now, if you want to build an algorithm for this, what you do is you have to expand now the finite element solution in a typically Lagrangian or nodal basis of functions. Let's call them phi I. And so you can write down the unknown function at time t as a linear combination of these unknown coefficients ui of t times these basis functions phi I, which are the typical het functions or tet functions as they're called. And then if you introduce now the mass matrix M, which consists of these L2 inner products, and the stiffness matrix K, then you end up with this well-known second order system of ordinary differential equations. So this is a finite dimensional system, of course. So M is an n by n matrix and K as well, and both are symmetric and positive. And here I'm going to make an important assumption. I'm going to assume that the matrix by something that is called mass lumping. It's a standard technique. This is to avoid that you have to invert the matrix M at every step. So we're assuming that M is diagonal. Just as a side remark, if you're using discontinuous Galerkin methods, then this matrix M would automatically be block diagonal with very small blocks. So it would already be like a diagonal matrix, essentially. So now if you want to fully discretize a method, you have to choose the time discretization. So for instance, I'm going to choose now the leapfrog scheme. This is the simplest and the most popular scheme for the wave equation in second order form. It's also very efficient. It's a very good scheme. So I like to point that out because usually when we present methods to students like Euler's method, well, nobody really uses Euler's method. But this method is very simple, but it's also extremely good, very powerful and efficient. So we replace the second order time derivatives by the second order finite difference approximation. So we now have the solution un plus 1 minus 2un plus un minus 1 divided by delta t squared here. And this is an approximation of the second order derivative. And so we end up with this algorithm here. So this is the algorithm that tells us if I know the solution at time step tn and tn minus 1, how to advance to the solution at tn plus 1. All right. But the question is, how do we choose? Hello?
It's okay, we hear you. But
sorry. So how
the sound is not the sound is not stable sometimes. Okay.
Okay, sorry. So how large should delta t be? This is a question, and this is a question you can ask, and the answer to this was given by, well, one answer was given by these three gentlemen here. So this is Richard Courant and Friedrichs and Levy, and they wrote this very famous article that's now almost 100 years ago. So it's an interesting point that this article is actually was written before computers were actually built. And they already asked this question: if you discretize a finite difference is actually a PDE in a space and time, how do we have to choose the mesh size in time with respect to the mesh size in space? And so they looked at this and they came up with this rule that is now called the CFL condition for the wave equation. And essentially this rule says that the space-time mesh has to be chosen such that the domain of dependence of the numerical solution contains the domain of dependence of the exact solution. If you imagine you were an observer at some point, then the solution at this point in space and time will depend on the path of the solution in what's called the light cone sometimes. So everything that's outside, you don't care, but you have to see everything that's inside. And this condition essentially is saying that the numerical solution sees all the information that the exact solution sees as well. And for this, it's important that you do not choose a time step that is too large. So these people did not argue about numerical stability because they did not implement this, but still they came up with a concept which nowadays is standard in numerical analysis for stability. So how important is this? So their condition is that you have to choose delta t equal to delta x. So the time step has to be equal to this space. So let's see what this means. So here I'm going to show you a very simple simulation in one dimension. So this is a very simple coarse grid. I'm looking at this so it's on purpose very simple, and I'm choosing here a delta t equal to h. So h is delta x if you want, and delta t is a time step. And here we see there's no problem, the wave keeps propagating back.
Please, one moment. I don't know if everybody is, I'm just seeing the last slide with CFL condition.
Yes.
Do you change this slide? No.
A little bit, yes.
Okay. I have a problem with my computer. I'm sorry.
Okay, no problem. So this was with CFL equal to 1. If I increase the CFL to 1.05, so just a little bit, this means I take a time step a little bit bigger, then what I see is the method, the numerical method becomes unstable. Okay? So we see that this is a very tough boundary, and we really have to choose delta t equal to delta x. Now, what about a locally refined mesh? So here I took the same mesh, but here, I don't know if you can see my mouse when I'm moving it here, but here around x equal to 1, I took two elements and I refined them. I made the mesh twice finer, 2 times finer, okay? And now I've used the same time step as before, just to see if it had, what is the impact. And if I do this, well, immediately the solution explodes. So I see it's very unstable. So I cannot do anything. Then I can say, okay, I choose a time step that's a little bit smaller. I try that, but again, the solution immediately explodes. And now I choose a time step which is almost half what the time step was before. And again, it still becomes unstable. So now I choose the time step which is exactly 1/2 of the time step at the beginning. And this is exactly what I did with my mesh because I refined by a factor 2. And what I see now is the solution is fine again. So the message here is that if I have a mesh and I locally refine even just 2 or 3 or 5 elements, I have to take a small time step everywhere in the entire mesh. Okay. And this is what people usually do. And so my talk is basically about this. How can we overcome this problem? Because of course, this is a huge waste of resources. If you have a big mesh and you have a few elements which are very small, and now you have to take a small time step everywhere in the entire mesh just because there are a few elements that are small. So the idea is, how can we overcome this? So this is, and I've written here two equations. These are both the wave equation. I've written it either in second order form or in first order form as a system, but it doesn't matter actually. So the point of this talk is really, how can we overcome what's called geometry-induced stiffness? So we have a mesh, and in some parts of the mesh, they're very, very small elements. They're highly refined. And because of this, we have a time step, which we are forced to take a small time step everywhere. And this is a big waste of resources, and it's a big bottleneck. So what are the solutions that people have tried? So there's one approach which is called an IMEX scheme, implicit explicit. So the idea is to have an explicit scheme outside in the coarse region, and the refined region here in red, you would do an implicit method. So you have an implicit method and outside an explicit method. If you do that, then you do not have stability problems. But of course, an implicit method means you have to solve a linear system at every time step. Okay. This is an approach that various people have tried, for instance, Piperno or Jan Verweer or others. The second approach is to be fully explicit, and there you take a smaller time step in the red part and a bigger time step outside. So you take a big time step where the elements are big and a small time step where the elements are small. And the third approach is called local exponential integrators. Basically, it means that you solve the ODE in the refined region exactly. So you don't have to invert a system, but you have to compute the exponential of a matrix, which is also quite cumbersome. So I'm going to talk here about explicit local time stepping. So everything I do is fully explicit. I do not solve any linear system. And the goal, of course, so I do this for two reasons. The first reason is because explicit methods, people really like them for wave propagation. They're standard for many reasons. They are very popular, they're cheap, they're efficient. And of course, it's very easy to parallelize them. So this is the goal. I want to develop methods that are fully parallel and that are very efficient, even on thousands of processors. Okay. So there are many people who have worked on this, and I don't want to go through all these, but maybe I make just a few points. So first of all, I'm not the inventor of this idea. Of course, many people have realized this before that have tried to get around this. And there are different methods that people have tried for doing this. For instance, there's work by Collineau and Joly and others from the early 2000s. Piperno has worked on this. And there's also, maybe you've heard of this approach, it's called ADER, DGs for discontinuous color. ADER is an alternating direction approach. They call this, basically that's a special DG method, discontinuous converting method, where every element has its own time step. So it's very flexible, but again, it's not so simple to use, and it forces you to use a very special discretization of space. So the approach that I'm going to show you, I do not tell you what you do in space. You can do finite difference, finite element, discontinuous Galerkin. I don't care. It doesn't matter. There also, then here there's a work by Constantinescu and Sandu, for instance. This is multi-rate. So multi-rate in the ODE community, people call these usually multi-rate methods. So multi-rate because the different unknowns advance at different rates, take different time steps if you want. This comes from chemical reactions. When people simulated chemical reactions, they had certain species that were very slowly varying and some were very fastly varying. And then they had to choose different time steps for these. Then this is some reference to my own work. This is work with Julien Diaz, where we proposed the first local time stepping method for leapfrog. So LTS is local time stepping, LF is leapfrog. We also did this and later with Theodora Mikova on Adams Bashforth. And here at the end, I've mentioned, so there's also a line of work that is becoming also quite popular. I think the main person behind this is Joachim Schöber from Vienna. So this is space-time DG. So space-time DG is also not a new idea. Space-time just means that you take the partial differential equation in space and in time, and then you derive a weak formulation in space-time. So if you do this, usually you have an implicit method in time. But there are people who are able to get explicit methods by doing what they call tent pitching. And this is to maintain causality, because you're not allowed to advance in one part without advancing in the other part, because the information has to propagate still in, let's say, a physically plausible way. So there are also these methods. So there are many people who try these things. And I'm not going to, what I'm going to do now in this presentation first, I'm going to look at how to derive a local time stepping method that is based on the explicit Runge-Kutta schemes. And this is why I, of course, you can do it for leapfrog as well. And I also do leapfrog, and I'm going to show you leapfrog a little at the end. But here I'm now going to look at Runge-Kutta. Runge-Kutta has the advantage. Runge-Kutta methods are very robust. They're very standard. They're one-step methods, so you have no starting procedure. If you want to adapt the time, it's straightforward. And I want to point out there are low storage versions available, but if you do not know about this, you can forget about this. Low storage versions are special Runge-Kutta methods where you do not have to store all the intermediate stages. Also for Runge-Kutta, I'm not the first one who proposed this. Other people have proposed this before, for instance, Grote et al. Or Liu and Li and Hu. So other people have tried these kind of things, but all these methods were low order methods. And here's a quote by Geer and Wells. So if you're interested in this subject, I recommend that you look at this old article by Geer and Wells. And the availability of extrapolation from past values is an advantage for multi-step methods over Runge-Kutta methods in the multi-rate context. So just to explain, so you have to imagine a Runge-Kutta method. You imagine you want to advance in time and you know the solution here. And now in one part of your domain, you're going to take a big step. In another part, you want to take small steps. The problem is, of course, that the solution is connected. You cannot just take a big step here because you don't know the solution here. And you cannot just take small steps here because you don't know the solution here either. So you're sort of, it's the chicken and egg problem. So I want to try to show you how you can overcome this, of course. So I want to show you how we can derive now explicit LTS method based on Runge-Kutta. So I'm taking, this is my model problem, so I can rewrite the wave equation in first order formulation. I do this because Runge-Kutta methods are based on this formulation here. So again, this is just to remind you that the matrix B, essentially it contains my stiffness matrix. It contains the inverse of the mass matrix as well. And I have, again, these locally refined regions. And because of this, I know that my time step, if I don't do anything, my time step will be constrained by the smallest elements in the mesh. Okay. So this is just a reminder. I assume that everybody knows what the Runge-Kutta method is. But let me just remind you, if you have also to show a little bit the notation, introduce the notation that I'm using. So Runge-Kutta method for an ODE of the form y prime is equal to f of y. Usually you have different stages. They're described here on the left, K1, K2 up to Ks. This is an S stage method. And each stage depends on the previous stages. And also, and is evaluated at also at the nodal values, which I'll here Tn plus these constants Cs, C1 to Cs. C1 is always 0. And at the end, I take a linear combination of all these stages. They are all slopes, if you want, of the solution at different points. And I take a linear combination, then I can advance the solution from yn to yn plus 1. And this is called the Butcher tableau. This is the shape it has if you have an explicit method again. So, and also every Runge-Kutta method has an underlying quadrature formula. What I mean by this is very simple. If you take this function f, and you assume that f depends only on time and not on y of t, then the solution is simply yn plus 1 is yn plus delta t, and then you have sum of bi, these are the weights, times f evaluated at tn plus cs delta t. So it's just a quadrature formula. And of course, this quadrature formula also needs to have at least order k. Okay, so now we start to derive a new method. We want to derive a new method. So this is the local time stepping method. How do we do this? So the first thing we do, we split the unknowns. So we have some unknowns which are associated with a coarse part, which is blue, and some with a fine part, which is red. I want to emphasize there's no special data structure here. It doesn't matter which order, and if you want, you can have different red regions. It doesn't matter. And we do this formally by introducing this matrix P. So we introduce the matrix capital P, and P is a matrix which has only zeros and ones on the diagonal. And every time there's a 1, it means that this is an entry that belongs, an unknown that belongs to the fine part of the mesh. And if it's a 0, it belongs to the coarse part of the mesh. So I can write y as I minus P times Y, this is the coarse part, plus P times Y, which is the fine part. You could also call this a partition of unity if you want. So then I can rewrite the ODE that we have down here. You can rewrite it. I have done nothing so far. And so I have this expression. I can also integrate this formally exactly. So I write down the exact solution. Can you see if I move my mouse or you cannot see this?
Yes, we can.
Ah, very good. So I can rewrite the exact solution. So this is a solution at time, I'm at Tn and I want the solution at the new time step. And so this is an exact solution formula. I'm just integrating the ODE. And in blue, we have the coarse part. In red, we have the contributions from the fine part. And so what I'm going to do, I'm going to approximate these two in two different ways. So first, I'm going to look at the coarse part. So the coarse part, this is the coarse part we had on the previous slide. And now I'm using the fact, so I'm going to do this now specifically for Runge-Kutta 2. So Runge-Kutta 2, the underlying quadrature formula is the trapezoidal rule. So the trapezoidal rule, you can see this here. Sorry, you have the weights, which are 1/2 here, and the nodes are 0 and 1. So we're going to use the trapezoidal rule to approximate this integral here. So if I do that, I end up with this. So let's go through this. It's not as hard as it looks. I'm looking first at the first part. This is the more complicated part here. So all I have is here b I minus p. So this is the exact integral. And now I use the trapezoidal rule. So I have the length of the interval, which is psi delta t over 2. Psi is a parameter. Delta t is fixed. And so I have, I evaluate the function at Tn. So this is b I minus p y Tn plus the function at the end of the interval. This is the quadrature formula. The problem is, of course, I don't know y at the end of the interval because I haven't solved the ODE yet. This is a formal thing. So now I have to do a second approximation, which is I'm going to replace y by its Taylor expansion. And I'm going up to order 2. I need to go up to order 2 to maintain the order. So I replace y at Tn plus psi delta t. I replace this now by the Taylor expansion. So this is what you see here. So the first term, I have psi delta t over 2 bi minus p yn. This is the same term we had up here. Then I have bi minus p, and now comes the Taylor expansion. So I have yn plus the derivative plus delta t times psi times the derivative at yn. But y satisfies an ODE. So now I'm using the ODE. The ODE is, well, y prime is b times yn plus fn. So I put that here, and I'm stopping. I don't need to go higher. And now I can regroup terms, and I end up with this expression here. So this is how I approximate the coarse part. And now finally, this is just, this is not very important, but I want to mention this as well. F, again, F, remember, is known. It's just the right-hand side. And we are going to interpolate, in the coarse part, we also interpolate this by a polynomial. This is to avoid that we have to evaluate f at all these intermediate steps, as you will see in a second. So now we know what to do in the coarse part. Now we come to the fine part. The fine part, actually, we don't do really any approximation at this stage, but the approximation you will see comes in a hidden way. So I take the exact integral you can see here, and the only thing I did is I replaced y by y tilde. Y tilde is going to be an approximate solution. It's not the exact solution, and I will tell you in a second how we get it. So once I have this approximation as well, I can combine the two that I had, the blue and the red part. I can combine everything. This one, this is just this is the right-hand side where I've replaced f by q, this polynomial. It's just known. And I've replaced here the fine part. And here you see there's still this error. This is the error that we make, the truncation error if you want. And now I'm going to ignore this. I'm going to drop this term because I'm only deriving a method of order 2, RK2 method. And to get this method, I want this method of order 2. So I'm going to drop this. And so now I can define y tilde. And how do I define y tilde? So this is the part that is a little tricky if you want. I define y tilde such that y tilde is the exact solution of this ODE here. And the exact solution of this ODE is nothing else than the formula that you can see here, where I dropped O of delta t cubed. So let me say this again. So this is the exact solution formula. If I drop this O of delta t cubed, then I have a formula, and this formula is now going to be the exact solution formula for this modified ODE. So this is an approximate ordinary differential equation. It approximates the exact one. You can see this actually. So tau is now, tau replaces time between tn plus 1. So tau corresponds to psi times delta t. So for instance, if I look at the, for instance, here at the first term, then I see here in the exact solution, I have psi delta t times psi delta t over 2, which is the same if I call this tau, it's tau squared over 2. And if I differentiate this with respect to tau, then I get simply tau times, this is the term here, byn plus fn. So the first term that you see here, this is just tau times bi minus pyn. And if I differentiate this with respect to tau, the tau drops. This is the tau squared over 2 and so forth. I can do this for all. So if I integrate this equation here exactly, then its exact solution formula is this formula here without the O delta t cubed. So this is the idea. So we have this slightly modified ordinary differential equation where we've made some approximations. Now, of course, we still have to solve this. And the idea is now we're going to solve this ODE. We're going to solve this with, again, with the Runge-Kutta 2 method, but with a smaller time step. And the smaller time step, I'm going to call delta tau. So this is what we do now. And so I know there's a lot here, and I'm not asking you to understand this algorithm, but I just want to explain the principle. So we have now, we took the exact ordinary differential equation. We split it into a coarse part and a fine part. In the coarse part, we use the quadrature formula and we use the Taylor approximation. In the fine part, we did nothing essentially. This way, we obtained a slightly modified ordinary differential equation. And this ordinary differential equation we now solve with the same with the Runge-Kutta method, but with a smaller time step. In this time step, I call delta tau. So we have a smaller time step delta tau, which is the global time step delta t divided by p. And this little p that you see here, this is always going to be the parameter, how many local steps I take for one global time step. So I take global time steps of size delta t. And if let's say little p is 3, then for every step here, I do 3 steps here, and then they meet again. And then I have again 1 step and 1, 2, 3 like this, okay? And if I do this, I get this algorithm here. So maybe if you see this, you're going to ask, well, okay, but why is this a local time stepping method? I don't see what's the point. The point is that what you see is that everything that is in blue, that is in the coarse part, is computed only once. This is computed only once. And all the local steps, these are the steps in the loop here. These steps, they always involve b times p, But b times p, this means I'm only taking the local degrees of freedom. I'm only taking the unknowns that are inside of the local region, and then I multiply by b. So the effort, the computational effort is always in using the matrix B, multiplying by B. So these are all local multiplications. So I have 2 multiplications that are in the coarse region, which I have anyway, because I have an RK2 method. These are these 2 multiplications here. One is here and one is here. And then I have little p multiplications, but they are all local multiplications. These happen only in the fine part. There's nothing happening in the coarse part. Okay. And you can show that this method in the coarse region is nothing else than the standard RK2 method. Why? Because we didn't do anything else but what RK2 does anyway, which is exactly using the trapezoidal rule. Okay. So the strategy I just showed you, you can use this for any explicit Runge-Kutta method. The idea, so I showed it to you for RK2, you can do this for RK3, RK4, etc. And we can, and of course, I haven't proved anything here, but we can prove that this method, the new method that we get, indeed has the same order of accuracy as the original Runge-Kutta method. Okay, and you can also, so this is what we showed here. We also prove that it's convergent in the ODE sense. In the ODE sense, this means it's convergent on a fixed mesh. I fix the mesh and I let delta t, the time, go to 0. Then it's convergent. This is not convergence in the PDE sense, which would mean h and delta t both go to 0. Okay, and we can also show that in conserves the linear invariance. This is important for certain applications, but it's not so important. So I want to show you now an example. So this is a typical 1D example that I use to test, that we use to test these methods. So what I do is I take a one-dimensional interval from 0 to 6, and in the middle third, in the center third, so this is from 2 to 4, I'm going to put a refined mesh. This is the exact solution. It's given. It's a very smooth, nice solution. Here I'm using actually discontinuous Galerkin methods. I have P2 finite elements. And I'm using, I'm even adding a little bit of damping, which I can do, of course, with the Ranglakada method. And here you can see, and I'm using different degrees of refinement. So what happens, you can see it on this mesh, you can see the coarse region here between 0 and 2 and between 4 and 6. And inside I have the refined region. Here it's locally refined, and here's degree 2. So this means now my method, for every step in the coarse region, I take 2 steps in the fine region. And we obtain the optimal order of convergence that we expect, which is your third order convergence, because we have P2 elements in space and an RK3 method in time. And you can also increase little p. Here I have 5. So this means for every step here, I have 5 little steps in here. Or you can even do 11, it doesn't matter. So this means I have a locally refined region, and I'm always using the optimal CFL condition. What this means is I'm taking the largest possible global time step that is allowed by the mesh outside. So it means I'm not paying any price because I have a locally refined region, and everything is explicit. I'm not solving any linear systems here. Okay. Here's a 2D example. If you remember the mesh from the beginning. So if I use this mesh here, I have this is let's call it a screen with a little slit, and I'm sending a wave on this. Again, I have a little bit of damping, but again, it's just for illustrative purposes. Here I use again, a third order Ranglakada method. I have again, P2 finite elements with mass lumping, and the ratio between the coarse and the fine is 7. Here, people often ask me, how do you know where is green, not green? We don't know, we just choose, it doesn't matter. So the user, you can also have a program that decides, okay, these are my coarse elements, and all the elements that are smaller, we just paint them in green if you want, okay? And the green ones are the ones where we're going to take smaller steps. So in the green ones, we take 7 steps. For every time step in the coarse region, we take 7 steps in the fine region, okay? And so here you can see the simulations. You have a wave that comes, it hits this panel, the left front just moves away. Now it hits the slit. You can see also how little piece gets through, and you can see very well how the wave propagates. Also, you do not see any kind of strange effects or reflections at the interface. There's no interface, in fact, between the green and the white region or the blue and the red region. Okay, so this works very well. So the same idea. So just to show you again, so the same idea works also for the leapfrog method. So the leapfrog method, this is a method that people typically use when there's no damping and when they use the second order wave equation. So you leave it as a second order wave equation. Here I've already removed the mass matrix, so I factored it out by introducing this A. And I can do this because, again, I always assume that M is a diagonal matrix, essentially, okay? So because if M is not diagonal, I have no explicit time stepping anywhere, then I need this to be able to do explicit time stepping. And so you can do exactly the same kind of approach. I'm not explaining it in detail here. And then you get a local time stepping method, which is second order accurate. And it's also energy conserving. You can prove that. And we can also go up to order 4, order 6, whatever order you want. And I've written the algorithm here, again, just to show you that it's very easy. If you want to test this in MATLAB, it's just 5 lines of MATLAB. It's nothing fancy. So this is the standard leapfrog approach. So yn plus 1 minus 2yn plus yn minus 1 by delta t squared. But now this is replaced by this term here, and this term here corresponds to calling this function here. And this function is just, here we have a first step because it's a leapfrog method, it's a 2-step method. So the first step is just a Taylor expansion. And then we have the p minus 1 remaining steps. And this is the standard iteration from the leapfrog scheme. Okay. So it's a very simple method. It's very easy to code. But again, the trick is that all the effort, the computational effort in the coarse part is done here, is only done once. And everything that happens inside here happens only in the refined region, because here you see you have A times P. And as soon as you multiply with P, P selects only the unknowns in the refined part of the mesh. So when you multiply by A, since A is a sparse matrix, this means you're only multiplying locally with the vector, and you don't have to do a global matrix vector multiplying. Okay. So we did this method. This method actually is older. We proposed, I don't know, yeah, we proposed this method together with Julien Diaz in 2009. So it's fairly old already. And we proposed also a multi-level approach in 2015. But it was very hard to prove anything about this method. So it took a long time. And many other people have tried also a similar method. It's very hard because the difficulties, you cannot use standard proof techniques. And the main difficulty is you have this P which projects the solution, the global solution on this refined part, but then you also have operators like gradients or Laplacian operators, and they do not commute. You cannot take a function, project it, and then apply derivative. It's not the same as applying the derivative and then projecting it. And also Moya and Ferver had seen for 2011 that sometimes you take local time stepping methods, you take two methods in space and time, which are, let's say, order 2, but then you combine them in this special way. It was for an IMAX method though, and they ended up with a method of order 1. So you have to be very careful that you do not lose the order. But in the end, together with Stefan Sauter from the University of Zurich and Michaela Medin, who was my student at the time, we proved, well, now it's not such, about 4 years ago now, we proved that actually, we proved convergence in the PDE sense. So this is a rather long and technical proof. And we were able to prove that the discrete solution, local time stepping solution with the leapfrog method indeed converges optimally. So in the L2 norm in space, and here L infinity in time, we expect h to the m+1 if you have polynomials of degree m, and delta t squared because it's a second order method in time. However, in this proof, we were very proud, I have to say. This proof is the first proof I know of where where one shows that an explicit local time stepping method converges in the PDE sense. So as h and delta t both go to 0. And but still the problem was that this constant CT, actually it's still dependent on little p. This was annoying. We were not able to remove this at the time in the proof. So what this means is that if you have a mesh and you have, let's say you have a mesh that is five times refined in the local region, then we can prove that as you refine globally in h and delta t, you have optimal convergence. But if you now decide to have, instead of 5, 17 or 27 local steps, then this would have an impact on this constant here. And it took us a while. We only proved, I'm going to say that we only proved very recently, we found a way around this, but this is a very tricky and technical issue, which I do not want to get into today. So here I want to show you, we're getting closer to the end. I would like to show now some numerical examples also on the parallel machine. So to show you why this is interesting as a method. So this was done as follows. So this was really the thesis of Max Riedmann. And so here's what he did. He took the local time stepping methods based on leapfrog that I just described. And he took a well-known code. It's called SpecFem 3D or 3D. And this is a spectral finite element code to do seismic wave propagation. So to do elastic waves, seismic waves in the earth. So it's a code you can actually download. It's free. And what he did then is he took the time stepping method and he replaced this time stepping method in the code by this new local time stepping method, which we knew is designed to be very good to parallelize. So we wanted to see this. And he, of course, he has to deal with issues like workload balancing and how to partition the mesh and distribute the work across processors. So he used for that this Scotch software. And if you're interested in the details, you will see this. You can see this in just JCP paper here. And so here, for instance, this was a simulation. We're simulating an earthquake that's going across Switzerland. So this is supposed to be Switzerland. Okay, I don't know if you know this. And so it's a very small country, actually. So it takes only an earthquake about 3 minutes to go across, a true earthquake. So, and we simulated this. So the simulation was with a mesh at the time with 350,000 elements, 23 million degrees of freedom. And so the point was the following. If he was using a homogeneous mesh, equidistant, if you want, mesh, then the computation would take 40 minutes. But instead, because of the local refinement, so the idea was that here you have the earthquake is originating. So there you have very complicated physics happening. You have a fault or very complicated things. So you would like to have a locally refined mesh here. To have a locally, so you have here a mesh. So this is why you can see it here. You can see that the mesh has a certain hierarchy. So you have very small elements here. Maybe there's some nonlinear effects. I don't know. So, but again, because of this, this forces a standard method to take very small time steps. So because of this, instead of 40 minutes, the computation would take 16 hours. This is very annoying for geoscientists because they don't want to simulate this once. They want to simulate it many hundreds of times. They want to simulate these earthquakes, or they want to solve an inverse problem. So the question was, can we actually overcome this problem with the local time stepping method? So what we do now, here we're using the hierarchical approach. So we do not just have one coarse region and one fine region, but we have all intermediate regions. So what we do is we have the coarse region, and then we take all the elements that are twice smaller. These are these here. So these are the global, the coarse ones, and we have about 5,600 elements, which are, if you want, half the size. Then these are about a quarter the size, etc., until the ones that are 32 times smaller. So they require delta T, which is 32 times smaller. Okay. Then for this mesh, you can compute by hand. You can compute the expected speed up for this special grid. You can ask, what is the best speed up I can get if in the perfect world? And the best speed up, so this means that you take for every time step here, you take 2 time steps here, 4 time steps here, 8 time steps here, etc. And you just count the elements and the number of time steps. And then you end up with a speed up of 25.5. So the best you can do is be 25.5 times faster than a method which uses a small time step everywhere. And so we try this, we implement, and this is what we got as a result. So what you see here, you see the parallel results. We increase the number of nodes. And here we look at the relative performance comparing to a method where here, so let's look at the first line. The first line here, this is on CPUs and there's no local time stepping. So the method, actually it's an explicit method, so it parallelizes very well, but there's no local time stepping. Now, when we added local time stepping going on these CPUs, we went up by a factor of 24. So it's very close to the 25.5. So the method got 24 times faster just by going from non-local time stepping to local time stepping. And then when we switched from CPU to GPU, we got another factor of 4 approximately. So we had a gain of about 100. So the method went 100 times faster by using GPUs, but mainly also by using these local time stepping methods. So this is very interesting, I think, for people in applications. So I'm coming to the end of my presentation. So I would like to take a little bit of time for the conclusion, because I want to say also a little bit about some very recent work I've been doing. So I hope I was able to present basically the approach that we have, which is to design explicit local time stepping methods. They're mainly interesting they were developed mainly for wave propagation. Why? Because this is because people in the wave propagation community, they like explicit methods, at least in the time domain, of course. And if you do not have damping, that means that you have an energy conserving problem. Then very often people like leapfrog type methods, and we have local time stepping methods that work for these. If you have damping, then you can either use Adams-Bashforth or more modern, maybe Runge-Kutta methods, which are typically used. They work very well. This is what I just presented today. These methods assume always that you have a diagonal mass matrix. So either you're using mass lumping, if you're using a conforming finite element method, or you have a DG method, or nodal DG, or interior penalty DG, some kind of DG discretization to discontinuous Galerkin. Then you have a block diagonal matrix, but the blocks are very small in size, right? Their size is just the number of degrees of freedom on one single element. We have proved now optimal L2 convergence rates for this local time stepping method leapfrog. But again, as I said here, this was still with CFL condition that depended on the number of local steps. And as I've shown you, we get also high parallel performance. So these methods really also in practice perform very well, and they are not very hard to implement in parallel. So here's some things about very recent current work. So this is work from the last 2 to 3 years, and there are also some extensions that I would like to comment on. So first of all, this point about having a convergent method, we were able to stabilize the method. So this is a little bit technical thing, but it's a very small modification of the method, and we were able to prove convergence under a p-independent CFL condition. So we have a stabilized version of the method, which has all the same advantages. It's 3-term recursion, energy conserving, etc., etc. It's a very small modification of the original method, and there we get a CFL condition which is p-independent, and of course we get optimal L2 convergence rates. This is very recent work that appeared last year in MAPCOM. Now, maybe let me come, the second point, maybe you do not like waves, maybe you're not into waves. Okay, so you can actually do the same thing for parabolic problems. So for parabolic problems, people typically think of using an implicit method in time. But in fact, there's a class of methods called Runge-Kutta-Chebyshev methods, which are explicit methods, and they're designed for problems like the heat equation, for parabolic problems. And we now, together with Asir Abdul and his student, former student, Giacomo De Souza, we designed a local time-stepping method that is specifically designed based on Runge-Kutta-Chebyshev method, so it's specially designed for parabolic problems. And to conclude, this is very recent work also. So these two last you can find on archives, but they're not published yet. So we also combine local time-stepping method with multi-level Monte Carlo. So multi-level Monte Carlo methods are methods that are hierarchical methods that are interesting for doing uncertainty quantification for stochastic wave equations. And so by combining local time stepping, which means that on every level, we use a time step which is adapted to the local mesh because we use coarse and coarser meshes, we're able to restore the efficiency of multi-level Monte Carlo, even in the presence of complex singularity for stochastic wave equations. So that's it. Thank you very much for your attention.
Thank you, Marcus, for this very pedagogical speech. And we see that your double culture and computer science and mathematics can give very, very beautiful results. Okay, if we have some questions, and is there some questions?
Yes.
Hedy?
Okay, thank you. Thank you very much. So at the beginning, you suppose that the border condition are defined in t equals 0. So in practice, for example, for seismic wave, I think that we can compute the value when t goes to infinity at the end of the seismic, at the middle of seismic, and because in practice we don't know the time, exactly the time when the seism starts. So if are there any results for waves when the border conditions are defined when t are in tends to infinity?
Okay, so this is
instead of t at time equals 0.
So it's a very interesting question. I never got this question. I have to admit, I'm not an expert in geosciences, so I'm thinking about it myself.
Me too. I'm not okay.
So so I understand. I believe I understand what you're saying. So what you're suggesting is that you have an earthquake, and because of this earthquake, you have a wave that's propagating, but you don't know the initial condition.
Yeah.
And so first of all, from what I understand, the wave equation, when people simulate earthquakes, usually the earthquake is generated by a forcing term, not an initial condition, but I don't know. It's a forcing term that is local. Still, if you wait until t equal to infinity, I mean, now the question is about the forcing term itself. It's the same, by the way, with an initial condition. If you just have an initial condition and you let time go to infinity, the wave is just going to go to infinity unless there's a wall somewhere. It's going to go away and there will be no wave left in 3 dimensions, right? But this is not what you mean. I think what you mean is that you have a forcing term that acts for quite a while, and you don't know the initial condition. Then you have this wave that appears sort of out of nowhere. It appears and then stays there for a while, but at some point it will also go away. The earthquake will vanish. So yeah, I don't know. I mean, here, of course, I'm supposing if you have an initial condition that it is known. And again, if you have the wave equation in an open domain, an unbounded domain, of course, the Earth is not unbounded, but if you have an unbounded domain and you have a local initial condition, then the wave will propagate away and nothing will come back. No. And if you have a forcing term, it's the same thing. The forcing term will generate waves, but only as long as it is active. Once the forcing term is not active anymore, the waves will propagate, but then they will go away and they will not come back.
No, I mean by saying infinity, by taking t very large, okay?
Okay.
So okay. This is the idea, okay? Another question.
Can I? Okay. Let me just comment. Okay, so this is, I just wanted, so there's one thing also I want to say, which is very important. The wave, if you get, so maybe your question is, let's say I want to simulate a wave, but I know the solution, not at t equals 0, but I know the solution at capital T. And then the answer is you can, because the wave equation is symmetric in time. You can go back and forth in time. So if you want, you can replace, basically you replace t by minus t, and then you can propagate backwards in time. And actually, the equation is going to be the same, because the second derivative in time will minus and minus will give a plus. So you can solve the wave equation backwards in time, and you can start at capital T, and then you will have the wave that will come back. And this is, I think, how people find the source of an earthquake. By taking the waves far away, they propagate it back in time, and then they can figure out where this wave originated from.
Okay, thank you. In your numerical scheme, you suppose that the matrix P satisfies P squared equals to P.
Yes.
So that means that your matrix P is not invertible.
No, it's not invertible. It's this P squared
doesn't
equals
cause any trouble in your numerical scheme. Because of non-invertibility of the matrix P.
No, because P is just a way of splitting the unknowns in a formal way, right? All I'm doing is I'm writing, here it is. So all I'm doing is I'm taking the vector y with all the unknowns and I'm splitting it in the coarse part and the fine part. And I want to do this formally, and I do this by multiplying by P. I didn't write P, but P is just it's a diagonal matrix with zeros and ones on the diagonal. And the zeros are in the coarse part and the ones are in the fine part. So you're absolutely right. P is not invertible. No.
When you say when you use for the matrix M, and you say that we need to inverse the matrix M.
Yes.
I think that is it not, we are not forced to inverse the matrix M, since we compute my, the product M multiplied by a column vector, so we can solve only a linear system.
Aha, I think so. Now I think what you're referring to, you're saying if I'm not using mass lumping, so if M is not diagonal, for instance, then I would have this M here, and then what you're saying, at every step, I don't have to invert M. I just have to multiply.
MU,
at least I think here, if you replace U double dot by UN plus 1 minus 2n plus UN minus 1, you will have an M that is sitting in front of you at the new time step. So I think you have to invert M. However, you can use a Krylov method, of course, or you can use a M is not a bad matrix. It's a very well-conditioned matrix, and you can use a method like conjugate gradients to invert M. It's not a problem, but of course it costs much more than a true explicit method where there's no M. If you use finite differences, there's no M. M is going to be the identity.
I mean that if you compute a matrix, if you give let's consider a matrix A, And if we want to compute a minus 1 multiplied by b, we solve only the linear system ax equal b.
Aha, yeah.
We are not forced to compute the inverse of the matrix A.
Ah, yeah. Okay, now I think what you mean is when I don't have to invert m when I'm to multiply with k.
Yeah.
Ah, yes. For me, because but you see, I argue the other way around. I say I assume m is diagonal, and if m is diagonal, computing the inverse of m is trivial. You see, this is why I can do this. But of course, if m is not diagonal, I would never do this. I would do what you're suggesting. You're right.
Okay, thank you very much.
You're welcome.
Is there other questions, please? Okay, I have a question, but because I'm not aware about non-uniform meshes with space and time, and when you give the result of a global convergence in the finite element sense, okay, I mean H and T of the step in space, the step in time must respect the CFL condition, or
yes.
Okay, then
but independent of the number of local time steps.
Okay, and H or delta T here is the maximum of the step. It's exactly what you said, I think, in your in the result.
So H is the mesh size of the. So when in our proof we have a mesh. We have a mesh where we have a coarse part and a fine part.
Exactly.
The coarse part is quasi-uniform, and the fine part is quasi-uniform, and then we have a ratio between the coarse and the fine, which is little p.
Okay, and in your result, it's this ratio that appear in your estimation, or in the error.
So you have to treat, because you see the numerical method is different in the coarse part and the fine part. So this is why it's not so simple. You have to treat them differently, but in the end, you get a global error estimate for the entire solution. And H and delta T are the global. So it's the coarse mesh size, and it's the delta T is the global time step.
Okay. Thank you. Is there other questions? Okay, thank you, Marcus, for accepting our invitation and for this very beautiful speech.
Very welcome. Thank you.
And I hope we can invite you again. Okay. Thank you very much.
Thank you very much.
Thank you very much. Yeah. Okay.
Thanks.
All right. So I wish you all a very nice day and nice evening, I guess, at your place.
Thank you, Marcus.
Okay.
Thank you.
Bye-bye.
Bye-bye. Bon séjour en forêt noire, alors.
Ah oui, d'accord. Oui, Nabil, bien sûr. Oui, je suis encore là. Tu m'entends encore? Oui. Merci beaucoup. Donc là, je serai, oui. Après, je vais encore aller en Angleterre. Je vais aller, je ne sais pas si tu le connais. Je vais visiter un collègue qui s'appelle Omar Lakis, qui est à Sussex. Je ne sais pas si tu connais.
Non,
tu ne connais pas. Non, Omar Lakis. Il est d'origine libanaise, mais il parle. En fait, il vient aussi d'Italie. Il est très par plein de langues. Voilà. Et puis, c'est tout pour l'instant. Et toi, tu n'as pas de voyage prévu pour l'instant?
Non, pas du tout. C'est un peu compliqué d'avoir des missions à l'extérieur d'ici. Donc, j'en profite quand on a quand même deux mois de vacances. Donc, je profite pendant ces 2 mois pour prévoir quelques missions en général.
Bien sûr.
Donc, ça sera en début d'été, en fait.
Je vais demander juste un truc.
Oui.
L'université où tu es maintenant, là, elle s'appelle AU, je crois, IA et le KAUST aussi.
C'est ça, oui. Donc,
C'est
l'université
la
de Suisse.
même?
Non, non, le KAUST, c'est près de Jeddah. Donc, c'est vraiment,
Voilà.
c'est sur la mer Rouge. Donc, c'est,
Ah,
et KAUST, c'est vraiment une université un peu spéciale. Donc,
d'accord,
qui, je ne sais pas comment elle est gérée exactement, mais
d'accord.
qui fonctionne complètement différent des autres universités saoudiennes. Donc,
Ah, d'accord,
ils
ça, je
ont,
savais pas.
ils arrivent à avoir des budgets pour attirer des enseignants de grand renom. Ils ont des prix Nobel, des,
D'accord.
et, et, et évidemment, donc, ils arrivent aussi à prévoir des bourses pour des étudiants. Les meilleurs étudiants, pratiquement en Arabie Saoudite, partent à KAUST pour faire leur thèse s'ils ne partent pas à l'étranger.
D'accord, ça, je ne savais pas. D'accord. Et c'est à quelle distance de là où tu es toi?
Ah, c'est à peut-être 1400 kilomètres.
Ah oui, 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 ah, c'est loin. C'est grand, hein, chez
Ah
vous.
non, non,
Ah,
c'est un vrai continent, l'Arabie Saoudite. Hein,
j'imagine. Oui, j'ai jamais été, mais je connais.
et c'est un très beau pays si on ne connaît
Ouais,
pas.
je
C'est
sais.
très diversifié, il y a de très, très beaux endroits. Donc, c'est vraiment un pays à découvrir.
Ah, j'imagine. Absolument. Très bien. Alors, je vais te quitter maintenant.
Merci, merci à toi. À très bientôt.
Merci.
Au
Je suis
revoir.
très content d'avoir fait ça. Merci, hein, et
Euh,
bonne
et
soirée.
moi,
Au
je suis très
revoir.
reconnaissant que tu l'aies fait aussi.
Et c'est
Merci.
très volontiers. Au revoir,
Au
hein. À la
revoir.
prochaine.
À bientôt.